Okay, let's start. So, last lecture we were looking at this basic common emitter amplifier, and we had said that there are several important parameters: gain, input and output resistance, maximum output swing that you can get, cutoff frequency, stability. And in the context of gain and input and output resistance, we had seen that there's a fundamental trade-off between gain, input resistance and output resistance, which is described by this particular relationship. So if you want a high gain, you'll have to sacrifice either input resistance or the output resistance, or other way around. If you want a very high input resistance, either you'll end up getting very high R0, or you'll have to compromise on the voltage gain here. So there's a fundamental trade-off, and the kind of performance that you can get out of a common emitter amplifier is ultimately limited by beta. If beta is high, your ability to get high gain, high input resistance and smaller output resistance is better. If beta is low, then your ability to get these desirable quantities is limited then. Okay, so that's the importance of beta that is there here. Now, there are other important parameters as well. Today, what we are going to see is output voltage swing. The question that we are asking is, how large a output swing can we get here? And what are the parameters that affect the output swing? And also, as you will expect, that whatever is a desirable quantity, if you want something large, something good for it, it will come at the expense of something else. Okay, so it's almost always the case in engineering that if you want something which is good, high value, you'll have to compromise on something else. So if we want a high swing, high voltage swing, then we'll have to compromise somewhere else, and we have to understand what that particular trade-off is. And so why are we interested in high swing, V0? Well, if you look at this particular picture here, ultimately you're building an amplifier to deliver power to the load. And so the amount of power that you're delivering to the load, let's say if it's sinusoidal, is V square, V naught square by 2RL. So if you want to deliver high power to the load, well, you want large V naught to develop here. The other reason is, remember, the power that you're delivering to the load is eventually coming from here, VCC. And so power is being taken from here and delivered to the load here. So now the power which is taken from the supply will be VCC multiplied by some current. And if you take that power, that's the input power, and the output power is V0 square by RL. And if you divide the two, that's the efficiency of the amplifier. And you would note that the efficiency of the amplifier would improve if V0 becomes as high as possible. Okay, so these are the things that we'll see later on, efficiency consideration. So today, what we're going to see is, what is it that limits V0? Why is it that I can't? It seems very straightforward that the relationship between V0 and Vs is gain, AV. And it seems straightforward that if I keep on increasing Vs, I should keep on getting larger and larger values of V0. But obviously the answer is not as simple. We know that there are fundamental limitations. There's a supply voltage here, VCC. In a resistive circuit like this, I can't get V0, which is above VCC, for example. So there are limitations. So let's go and look at it here. So today's topic is, what is the highest value of output voltage swing that I can get here? All right. So with that, let's start with looking at this particular node here. This particular node that is there here, this is where we want the swing. So let's look at this node. And this node, as you would realize, that when I don't apply any voltage here, no input voltage is being applied, this node has a certain DC value, which we call as VCEQ. The quiescent point or the bias point, collector, emitter, all capital letters indicating it's a DC quantity, VCEQ. Now when you apply a signal here, which for convenience we assume it to be sinusoidal, then as the sinusoidal signal comes here, then on top of the DC, there's a sinusoidal AC also riding on top of it, which is, let's say, if input is sinusoidal, then the output is expected to be sinusoidal. So V0 equal to V0M sin omega t. V0M is the amplitude of the sinusoid here. So what happens is my net voltage begins to look like this. The red line, it shows the net voltage here. So when there's no signal, 0, then it goes negative and then positive, and so that's the net value of the collector emitter voltage here. So the net value is always the DC plus the AC, and so this becomes the net value here. Now note, as I increase Vs here, what would happen is V0M would increase, and so the minimum value of VCQ would go even lower, and the maximum value of VCQ would go even higher. And this is what is V0M here. So one of the things that you see here is that the maximum collector emitter voltage at any point is the DC value VCEQ plus V0M. That's the maximum value. Okay. And the minimum value at any point is VCEQ DC minus V0M. Okay. So that's the maximum and that's the minimum. So the net collector emitter voltage is varying. Now we know that the minimum collector emitter voltage has to be greater than VC sat. Otherwise the transistor will go into saturation and you'll start getting distortion. So this has to be greater than VC sat, which we've been taking as 0.2 or 0.25, 0.3, around that value, 0.2 let's say. So this is greater than this. So it tells you that the swing here, the amplitude of the output swing, will always be less than VCQ minus VC sat. It can't be more than that. If you try to force it, if you try to force a larger value of Vs and try to make V0M larger, what would happen is this minimum value that you see here would fall below VC sat, will fall below VC sat, and the transistor would be in saturation. Saturation meaning you'll start getting distortion, which I'll show you in a minute. So which means that for a given design, what is the highest value of V0M that you can get? Well, one of the constraints that you're seeing is the highest value of V0M that I can get is VCQ minus VC sat. Since VC sat is very small, so roughly the highest value that you can get is VCEQ. So that brings out also the importance of VCEQ here. Also note, in the last lecture we had written this expression for gain. One of the expressions for gain we had written, open circuit voltage gain, is VCC minus VCEQ by VT. Now you can clearly see a trade-off existing between the voltage gain here and V0M. If you want a high voltage gain, what would you like to do is push VCQ to as low a value as possible. You would like to make this VCQ small to get a larger value of gain. Well, if you make VCQ small, then the output swing that you can get also becomes small. If I make VCQ equal to 1 volt, well, 1 volt here, the maximum swing that I can get is 1 volt minus 0.2, which is 0.8. And accordingly, you can calculate whatever is the gain. If you want a swing which is higher, say I make it 2.2 here. So 2.2 minus 0.2 will give me 2 volt swing. But then when I put 2 here, the gain will fall. So you can see that, all these quantities, whether you look at gain, input, output resistance, there are a handful of parameters. There's RC, VCC, RB. They all depend on the same parameters. So if you try to influence one quantity, the other quantity also gets affected, and usually in a wrong manner. So if you try to increase VCQ to get high swing, well, the gain also falls down here. All right. So this is the picture that we have then. But note, I talked about the minimum value. I said that the minimum value, VCE minimum, must be greater than VC sat. So that's one limit. The other limit also comes from the upper side here. The maximum that you see here, VCE max, which is VCEQ plus V0M, this one. I can draw a line here, which is VCC, and we know that the maximum value cannot become larger than VCC. That's the upper floor. If there is a minimum floor here, then there's an upper ceiling also on VCE here. So what I can write is then, if I look at the maximum VCE, what I can write is VCE must be less than, maximum VCE must be less than the supply voltage here. So that's another limit which is coming, and this tells us that V0M has to be less than or equal to VCC minus VCQ. So it depends. It depends on how I bias. If I bias as you will see in the next slide, if I bias VCEQ close to VCC, then this may become the limitation. On the other hand, if I bias my transistor VCEQ close to the 0 here, then this may become the limitation. So it depends on how you bias, whether this eventually determines V0M or whether this eventually determines V0M. Okay, so let's look at that. So V0M then, what is the maximum output swing that you can get according to this picture is the minimum of these two. Either this will limit it or this will limit it. Whichever one is minimum, if either this point here makes the transistor go into saturation, or this point starts to get very close to VCC, either one of those will determine the swing here. Yes. I'll come to that. A linear approximation, I'll come to that here. Okay. So, as I was saying, if VCQ is too high, which means is very high, then what would happen is you'll start violating this limit first. On the other hand, I can have a situation where VCQ is too low and you violate this limit here. It starts to go into saturation. Right? So, what is the best way of biasing then? To get the highest possible of V0M, what should I do? Maybe that's the picture, right? I should bias it such that it's almost in the middle and I'm touching this limit and I'm touching this limit also. Then I will get the highest possible value of output voltage swing. And that value would be, if I neglect VCE sat, according to this picture, what I should do is, I should bias VCQ as approximately VCC by 2. Because VCE sat is small if we are talking about 5 volt or so. So if we neglect VCE sat, what we are saying is you should bias it in the middle. If you bias it in the middle, then you will reach this limit and this limit simultaneously, and you'll end up getting the maximum value of V0M would be equal to VCC by 2. So the highest output swing that you can hope to get in an amplifier like this, if your supply voltage is 5, the maximum output voltage swing that you'll get is 2.5. Or peak to peak swing would be 5. Okay, and this tells you that you should bias in the middle. You should bias in the middle. But let me warn you, as somebody just raised the issue, this is sort of neglecting any nonlinearity which may be there. We know that transistor is nonlinear. Right? Even before you reach a limit like this, there are important nonlinearity effects which start to set, and therefore this picture is not really valid. If you're hoping, so this is the conventional picture. In many books you will find that is written that what you should do is take an amplifier, bias it in the middle. Bias it in the middle with VCQ equal to VCC by 2. And then you'll get the maximum output voltage swing. You'll get a swing, V0M, which is approximately equal to VCC by 2. That's the conventional picture, but we'll see that not entirely true. Okay, so let me bring in some simulation results for you so that you can see what is happening here. All right. So here is an amplifier. Okay. Some amplifier, right? So the amplifier that we've been discussing, some values of RB, RC, VCC have been taken. So I'm not going to touch VCC. I'll keep 5 volt. I'll keep 5 volt. This VBB is 5 volt. There was no need to take a separate battery. I could have taken this node and connected it here as well. It's the same circuit. That's not an issue. RB also I'm not going to touch. Okay. So let's see how this transistor is biased. So I can take analysis, do a dynamic DC, which will tell me the bias point here. So you can all note bias point is here. This node is biased at about 0.72. So saturation voltage is about 0.2, so fairly close to saturation. Okay, 0.72. So that's where it is biased. What is the gain of this amplifier? Well, I can do, if you want small signal gain of this amplifier, you can do AC analysis. And you can look at V2 is our output node. I can plot it out. And the gain of this amplifier is 165. Fairly high gain because I've biased it very close to the edge of saturation. So 165 is the gain that we get. Okay. All right. Now, so let's remove this 0.721. Now I want to drive it with an AC voltage here. I want to look at how much swing am I getting here. Small signal analysis will not give you swing. Okay, so for swing, you have to do transient analysis. So I've applied a sinusoidal voltage here. As you can see here, it's 1K, 1 kilohertz frequency, mid-band. I've applied an amplitude of 10 millivolt. Okay, if you want smaller, I can make it smaller. We'll do that. So 10 millivolt here. So let me run, and the node that we are looking at is node number 2. Okay, node number 2. So let's do the transient analysis. I'm plotting it for 2 milliseconds, which means 2 cycles. And let me plot the V2. All right. Here. That's the output voltage here. Let's put it here so that you can see. Here is my amplifier. All right. So this is what we get here. Note what is happening. I drove it with 10 millivolt. 10 millivolt. Now what will happen to node 2? The voltage will go up and down. As it goes down, what has happened to my transistor? Gone into saturation. And you can see here, clipping. It's getting clipped. It's getting clipped, highly distorted. Now if I reduce it, so obviously I can't get, let me reduce the voltage here. 10 millivolt is too high. Let me apply 5 millivolt. Well, there's still, you can see here, still clipping. Still it is at the edge of saturation. So you can't even apply 5 millivolt. Maybe I'll apply, 3. Let's see. Okay. Looks reasonable. Sinusoid. Now, we don't judge whether sinusoid is reasonable or not on the basis of visual inspection. All right. Visually, does it look nice? Or visually, for a sinusoid, you may be able to look and say whether it's visually the signal is fine. If it were a speech signal, how would you tell whether it's visually? Okay. So there are other ways of finding out. So what you can see here, if you find that this is a reasonable sinusoid, so this gives you the net voltage at 2. Let me plot, instead of net voltage at 2, let me subtract the bias point here. So let me plot this one. The bias point is 0.721. So instead of that, let me plot the voltage here and plot this one. Okay. All right. So what is the swing that I can get now? It looks reasonable swing of how much? 0.47. 0.47 volts here. But interestingly, go here. Can you see something else happening? This is from node 2, I've subtracted the DC. I've subtracted the DC. So, normally I may have a capacitor which will subtract the DC. So this is what I'm plotting. So what is the swing now? How much is the output swing? The positive magnitude is how much? 0.472. And the negative magnitude is 0.511. Can you see that, the sinusoid is distorted? Ideal sinusoid means what? Positive voltage magnitude should be the same as negative magnitude. But now you don't have that. This is an indication. If you want very quickly to assess how much is the distortion, well, you look at the positive magnitude and you look at the negative magnitude. And if the two are substantially different, you know that there's heavy distortion. So in this case, there is distortion, 0.472 and 0.511, but not that large. They're reasonably close here. So now if I want higher swing, what should I do? What should I do to my amplifier? I want swing of, this to go up to 1 volt and this to go up to minus 1 volt. What should I do? Remember what is the problem? This VCQ was too close to saturation. So I need to move this VCQ up. How do I move it up? I don't want to touch any of that. So the very easy way to move it up is just reduce the value of the collector resistance. If I reduce the value of collector resistance, the drop here will change and the value of this particular node will go up. Okay, so let's look at, let me come out of this for a moment and let's say I change it to, let me run my dynamic DC again. So the value of this particular node is 0.721. So let me change it to say 1.16. 1.16. How do I know? Because I've run the simulation before. How much to change? So 1.16 is the answer. And where do you get? You get, can you see, it's almost in the middle. 2.5. The first two refers to the node, so I can remove this if that's causing confusion. So the voltage at this particular node is 2.5, almost in the middle. So a bias in the middle. What would you expect? I should be able to get a swing as large as 2.5. Okay, so let's see. So by the way, now that I've moved to 2.5, what else would you expect? Gain to fall or not? Okay, so let's see how much is the gain now. Analysis AC. Let's run it. Earlier it was 165. Now the gain is 95. So I've lost gain. The moment I shift VCEQ, I've lost gain. That's the price that you have to pay. Well, suppose we are willing to live with it. Let's look at the transient analysis. By the way, this is 2.518, so we'll have to subtract 2.518 from the value to get the swing here. Okay, so let's run the transient analysis. Now I should subtract 2.518. Okay, 2.518 to get the actual output voltage here. Okay, so let's run it. Okay. All right. So, well, we get lower swing. Why? Because I've applied a lower voltage here. So we'll have to drive, to get a higher swing, you'll have to drive a larger value of input voltage also. Okay. If the swing is fallen, for the same input voltage, the swing is fallen because we have smaller gain. Okay. So that was expected. So let's increase the value here. So instead of 3, let's put to, I don't know, let's put 10 milli. Okay, 10 milli. Let's put the values here. I get 800.8 volt here, and on the negative side, I get minus 1.136. Okay, you want to drive it harder? All right, 15 millivolt. Okay, is it distorted? This is minus 1.8. What does the theory tell you? Theory told you that you should be able to get 2.5, right? 2.5, your bias in the middle, you should be able to get, if not 2.5, maybe 2.3, maybe 2.2, close to that. What are you getting? Positive peak is 1.095, negative peak is minus 0.1892. This is almost like double, fairly distorted sinusoid, right? Now, so when we talk about swing, if somebody says, you know, peak to peak swing. So peak to peak swing is how much here? Almost like 1 and 1.89. So let's say close to 3. Peak to peak swing is close to 3. So somebody says, I got a peak to peak swing of 3. Somebody else says, I have peak to peak swing of 2. Is that a complete sentence? What should you always say? With how much distortion did you get it? If you got a peak swing of 3, peak to peak swing of 3, with what distortion? Because I can get a peak swing of 3 here, but with a high distortion. Somebody else may say, I got a peak swing of 2, but with a low distortion. So output swing has no meaning unless you specify how much distortion are you getting. You have to specify what is the level of distortion that you get here. Otherwise, simply saying I got, you know, I can drive it even harder. Well, 15, let's make it 20. What will happen? 20, let's do that. Now, well, what is the swing that I get here? Well, here I'm getting 1.37, and so if you calculate peak to peak, you'll get some 3.4 or whatever, right? 1.3 and 2.4. Oh, 3.7 or 3.8. So you say I get a swing of 3.8, but with how much distortion? With a larger distortion. So it's saying that I get a certain swing is not enough. You have to say with how much distortion am I getting it. So now distortion, why am I getting distortion? I'm getting distortion because my transistor itself is nonlinear. We'll see in a minute, transistor is nonlinear and I'm getting distortion. The other reason is that even if, let's say, the transistor had not been nonlinear, had been perfectly linear, it can't go below a certain limit. Below a certain limit, so you'll start getting clipping here. Okay? So the other thing that you must be seeing here is that on the negative side, I'm able to reach almost very close to the value. Minus 2.5 is the ideal. That's what you could have gotten, right? If this is 2.5, this would have gone, output swing would have gone to minus 2.5. On the positive side, you're not able to go to 2.5 at all. Okay. All right. So swing, this is not enough to talk about how much swing I get. One needs to talk about what is the level of distortion. So fortunately, our simulation programs also give you distortion. So there is it will calculate distortion. Okay. So let's look at distortion. So distortion, this is my output voltage here. And you can calculate how much is the distortion depending on how much input voltage you apply. The larger the input that you apply, the larger output voltage you'll get, and you'll get more distortion here. So I'm plotting, let me plot first this one here. All right, so I'm plotting 10 millivolt. You'll see it more clearly maybe if I change it to, yeah. This is, okay. So what has happened is, what is it showing? That I've driven a 10 kilohertz sinusoid with a magnitude of, how much did I put? 10 kilohertz sinusoid with a magnitude of 10 millivolt. 10 kilohertz sinusoid with a magnitude of 10 millivolt. At the output, ideally, I would expect 10 kilohertz fundamental frequency. What do I get? I get 10 kilohertz here. Fundamental is right here. I get 20. Can you see here? 20. I get 30, 40, 50, 60, and all that. All the harmonics that are there. I get a fundamental. The amplitude of the fundamental is about a volt. The amplitude of the second harmonic is about 0.1. And accordingly, you get all of them here. You can see the entire spectrum. It will calculate and tell you what are the harmonics present. Well, what we can do is we can add them up in a RMS manner here and plot what is called the total harmonic distortion. Total harmonic distortion, which will add up all of them and will tell us how much is the total harmonic distortion. Why is it doing like that? Well, seem to be stuck. All right, let's run total harmonic distortion, cumulative. Let's see, it adds up all this one here. 9.6. Can you see here the word 9.6? So it's adding up everything, all the distortion. So it gives you 9.6% total harmonic distortion. 9.6%, which means all of them, if you add up, is 9.6% here. Now you can see here, suppose I drive it with 20 millivolt, I'll get much higher distortion. Note the value. 17.7% distortion. So you can drive it with 20 millivolt input. Output would be even higher, but with a larger distortion. If you want less distortion, you'll have to apply less value of input voltage, 5. 5 will give you close to 4.8% distortion. Now when I'm applying only 5 millivolt input, the output would also be smaller. Okay, so we can get now all these things here. So let me sort of summarize what we have here. Okay, let's come back to, so we have a picture like this. Note, we took our amplifier. I've applied 1.1 here. 5 millivolt when we apply, 5 millivolt. This is the output that we get. Peak to peak value is 0.91. Peak to peak output voltage is 0.91. Harmonic distortion is 4.8%. When I apply 5 millivolt. Well, do you want higher swing? Well, I can apply a higher value of voltage here. I apply 10 millivolt. 10 millivolt peak to peak value is 1.84. Harmonic distortion is 9.6%. Well, if you want even higher swing, yes, I can give you higher swing by applying even higher value of input voltage. But remember, this will also go up. THD will also go up. So the point is, okay, so in the next case, what I've done is I've applied, remember this picture here, we said we'll bias it in the middle and we should be able to get 2.5 output voltage swing. Well, I've biased in the middle. I've applied 18 millivolt, fairly high. With 18 millivolt, all I'm able to get is 3.6 volt peak to peak. Instead of getting peak to peak, how much? 2.5. I get only 3.6 volt peak to peak and harmonic distortion 6.9%. Okay. So that's what I was telling you. This picture is simplistic. This picture is based on the fact that you have an upper ceiling and you have a lower floor, and that's all there is to an output voltage swing. We know that even before you reach the upper floor here, upper ceiling here, and the floor here, the sinusoid itself is getting distorted. Why? Because my transistor is nonlinear. So the sinusoid itself is getting distorted. Even before I reach, I've not reached maybe saturation, I've not reached, upper side, I've not reached the VCC here. And still the harmonic distortion is so large, 16.9%. Okay. So note that the first point that I'm trying to emphasize is when you say I'm getting so much output swing, you have to talk about how much harmonic distortion. So you can say 3.6 volt output swing peak to peak with a harmonic distortion of 16.9%. Or you say 1.84 peak to peak with a harmonic distortion of 9.6%. Okay, so that's the first story. The other one is biasing in the middle and hoping that you'll get 2.5 is not true. I'm not, 5 volt peak to peak. I'm fairly far from 5 volt peak to peak. I've already driven it to 18 millivolt. Yeah, I can drive it to 25 also. It's not going to make too much of a dent and it will get even more distorted. So there's no point in, driving it even harder and saying somehow I'll reach 5 volt peak to peak. I won't reach 5 volt peak to peak. Okay. So the picture is limited here. Now the other thing is, suppose somebody says my application requires a 10% harmonic distortion. I cannot have, for this application, my harmonic distortion should not be more than 10%. Okay. Now biasing it in the middle, 2.5. Biasing it in the middle gives me, for less than 10% harmonic distortion, almost close to 10%, 9.6, gives me a swing of peak to peak 1.93. Biasing in the middle. I'm showing you another biasing where I didn't bias in the middle. Note I biased it at 1.8. It's not in the middle. Okay? Not in the middle. What did I get? I got a swing of 2.5 with same harmonic distortion. So the other point that a notion that I want to dispel is that biasing in the middle is the best biasing that is there. That's not true. This is clearly showing you. If I'm interested in 10% distortion, less than that, 2.5 in the middle gives you only 1.93. Biasing at 1.8 gives you 2.5. 2.5 volt swing. So it gives you better. 1.8 volt gives you better, not the one in the middle. Okay? So that's not true. Don't think that biasing in the middle is the best way of biasing that is there here. That was a simplistic picture. But let's come back. Let's look at this in a little bit more detail. Why is the distortion occurring? What is the reason? We are finding what is the element of distortion that you see here. The positive swing that you see here is different from the negative swing. One visible way of looking at distortion. Okay. Positive swing is different from negative swing here. So let's see why it occurs here. Now, if you look at the output, how is the output generated? You remember how the amplifier works? We said the way amplifier works is you take the input signal here, the signal goes and modifies the base emitter voltage. The base emitter voltage, what does it do? Modifies the collector current, and the collector current flows through RC and develops the output voltage. So where is the distortion coming from? Where is the distortion coming from? Distortion is coming, this is a pure sinusoid. This is a pure sinusoid, but this is a distorted sinusoid. So where is it coming from? At what point, I painted the process. At what point does the distortion occur? This signal appears across base emitter. If this is a pure sinusoid, I should get a pure sinusoid between here, no problem. But here I don't get a pure sinusoid. So what happens? Is going from, what is happening is that the collector current, the AC collector current is getting distorted. The AC collector current is getting distorted. The distorted AC collector current flows through a linear resistor and gives rise to a distorted output voltage here. So why is the collector current getting distorted here? So let's look at it here. Note that we are talking about a sum of DC plus AC here. So the total collector current is DC ICQ plus a AC current IC here. And both of them always have to go as IS exponent VBEQ, which is DC, plus a small signal VBE here. This is the signal that we have applied by VT. So small signal base emitter voltage here is nothing but VS. So if I look at this relationship here, then the AC current IC is ICQ exponent VB by VT minus 1. From here we can write. Now you can see here, if I put VBE is, remember, is positive, the signal voltage here. So suppose I put, when VBE is 15 millivolt, I'm applying 15 millivolt plus 15 millivolt, IC comes out to be 0.78 ICQ. IC, collector current, AC value of collector current is whatever is the DC multiplied by 0.78. When VB is minus 15 millivolt, IC is minus 0.44 ICQ. You can clearly see now a distortion occurring. I would have wanted that when I have a signal here on the positive swing, whatever my IC increases, on the negative swing, the same decrease in IC should have been there. It's not, because it's an exponential function. You can see here IC is 0.78 ICQ, and on the negative side, when I apply minus 15 millivolt, IC is only minus 0.44 ICQ. That's the source of distortion, because of the exponential function here. On the other hand, suppose I had applied 2 millivolt, then IC would have been 0.08 ICQ, and negative side it would have been 0.74. Now it's much closer. Distortion is much less. So the source of distortion is this exponential relationship between the collector current and the base emitter voltage. That's the source of distortion. Okay. And this is a approximation that we have been using. IC is approximately equal to GMVB. So if my VB is very small, then this linear relationship would be okay. But when I'm talking about output swing, I'm pushing this, I'm no longer remaining at 1 millivolt or 2 millivolt. I'm pushing this input voltage here to higher values, and distortion becomes a very important phenomenon. Okay, so it's this exponential relationship that's responsible for distortion here. So this is what you find. If I apply 15 millivolt, the simulation results show you the collector current I'm talking about, AC collector current, much higher in the positive direction and much lower in the negative direction. That's what we saw here. Remember, positive collector current is 0.78 and negative is minus 0.44. And this is what you see here. So if you have to get rid of distortion, what should you do in this circuit? Note that large value of collector current will result in larger negative voltage drop, because there is a phase difference between the two, and this one will result in, so you get different peak values here. Suppose I want to get rid of distortion, what should I do? This distortion which is inherent in the transistor. Yeah, I don't want to touch VCC here. The design is fixed. Suppose I say the following. So, are you noting the following? I get a pure sinusoid here, right? I apply a pure sinusoid between base and emitter. This is a pure sinusoid. And the collector current is a distorted sinusoid. Now, suppose I ask you the question, what kind of a sinusoid should I apply here so that I get a pure sinusoid at the output? Suppose I could, by some means, apply a different kind of a sinusoid here between base and emitter. What kind of a sinusoid should I apply so that at the output I should get a pure sinusoid? Will that help? That my sinusoid that I apply here is a distorted sinusoid with a negative larger value. Why? Because note that in the negative side I was not getting enough current, so I apply a larger voltage. So now I will get a larger current, and the two will balance each other out. So at the base, between base and emitter, by some means, if I could apply a distorted sinusoid, then what would happen is this distortion will get cancelled by transistor's distortion, and at the output I'll get a nice sinusoid. Right? At the output, then the two distortions will cancel each other. Now the issue is, you must be wondering, I have a pure sinusoid. From this pure sinusoid, how do I get a distorted sinusoid? How do I get distorted sinusoid such that this distortion is cancelled by the transistor and I get a pure sinusoid? Well, the answer is actually very simple. Just put a resistor in the emitter. A very small resistor in the emitter. 20 ohm resistor. 20 ohm resistor, if I put here in the emitter here, note what has happened. I've applied 70 millivolt, very high, right? 20 ohms here. Look at what has happened to my collector between the base emitter voltage here. I'm plotting the base emitter voltage between here and here. Can you see the base emitter voltage between here and here? Look at the positive side. The positive side is, can you see positive side is much smaller? 19, and the negative side is 39. So by putting all I did was, I put a resistance, small value of resistance in the emitter. Small value of resistance in the emitter. I'm giving a perfect sinusoid, 70 millivolt, perfect sinusoid here. Between the base emitter junction, between here and here, what I get is a distorted sinusoid. I get a distorted sinusoid with smaller positive peak and with a smaller positive peak and much larger negative peak. The kind of signal that I was looking for, larger negative peak and smaller positive peak. That's the one I was looking for, and this is what I get. And what kind of result that we get? Well, so remember this circuit here, 1.16 and all that, and we got 1.93, 9.6% harmonic distortion. Let's put a resistor in the middle, in the emitter, small resistor, 20 ohms. I get a swing of 4.3 and a harmonic distortion of 9.6%. Same harmonic distortion, but a swing of 4.3. Compare that, 4.3 versus 1.93. I've almost doubled the swing. Yes. Why does it happen? How does it happen? Okay, so how does it happen? We'll see. First the mystery, right? First let the suspense be there for a moment. Enjoy the suspense for a moment. How this is the beauty of actually analog circuit. In the sense that, look at that, a small resistor, one resistor, that also 20 ohm, and you put into the emitter, and look at what it has done. 4.3 versus 1.93. Small changes in the circuit can result in very, very large changes in performance. Okay? So why does it occur? We'll see in a minute. Probably we don't have enough time for today. But look at that 20 ohm resistor, what it has done. So 20 ohm resistor, what has it done? So let's come back and see. So you are saying, okay, I get a swing of 4.3, much higher. I must have lost something in the process. Huh? I must have lost something in the process. You don't get something for nothing, right? That's never going to happen. So what did you lose in the process? Is right. What you lost in the process is, note what has happened. The signal that I applied here, I expected the entire signal was appearing across the base emitter junction. The signal that I apply here, some appears across the base emitter junction, the other appears across the 20 ohm resistor. And what causes amplification is what appears across the base emitter junction. So only a fraction of the input that you have applied appears across the base emitter junction. Obviously, the gain has been compromised. So you've sacrificed gain. Okay, let's see how much we sacrifice. All right, so let's go back to our simulation. Here, 2.52. So let's add a resistor. Let's put 20 ohm. All right, 20 ohm resistor. Let's look at the, see, 20 ohm resistor does not do much to the biasing. It's still 2.54. Earlier also it was biased in the middle. 20 ohm resistor still is biased in the middle, 2.5. So that doesn't, nothing really changes here. How much was the gain earlier? 165. No, how much was it? 95. So let's look at the gain. $35. The small resistor caused the gain to decrease by almost a factor of 1/3. 1/3, gain dropped by 1/3. And gain dropped by 1/3, but we got good swing. We got good output voltage swing. 4.3, which is almost coming close to now 5 volt. 5 volt was the maximum peak to peak swing that you can get here. All right. How does it work? Well, you guys are taking E250 also. Emitter resistance results in negative feedback. It results in negative feedback, which improves, I don't know whether negative feedback you discussed, which improves the linearity and reduces distortion. That's what we have done with emitter resistance here. It adds negative feedback, and negative feedback is a very, very powerful principle that we use in various places in circuits. There are things sometimes that you can't do. No matter how much I take this circuit and I modify it, I redesign with different RCs, different this, I'll never be able to get a swing of 4.3 with a distortion of 9.6. No matter what you do to this. What you do, no matter how you design, you'll never be able to get this. Negative feedback, by putting a resistor here, negative feedback allows you to carry out a trade-off. So the gain, which was 100 here, I sacrificed the gain from 100 to about 35 or so. We sacrificed the gain, and by sacrificing the gain, we got swing here. Okay. How does negative feedback work? This picture you must be seeing a lot, right? So here is a system, and you're taking a part of the output, feeding it back, and subtracting it, and you're causing negative feedback, right? So I want to put negative feedback in this circuit. I want to put negative feedback in this circuit, and the feedback that I want to put is in small signal. Let's say, so this is my small signal here. So let's see if negative feedback, you can see here, how negative feedback is operating. RE. Look at this picture here. So when I put RE here, this is my signal. This is my equivalent circuit. Can you tell which is Y here? Y is IC. Y is IC. X is Vs. So what do I have to do? I have to take Y, I have to sample the output, multiply it by something, and then subtract it from the input, right? So my Y is collector current, IC, small collector current. What am I multiplying with? RE. See, IC comes in and RE. And the drop here, is it subtracting from the input? Look, input was Vs and is subtracting from input here. Input earlier was dropping across entirely here. Now it is subtracting from it. So that's how you can see, this is why, this is your eta here, resistor, and this is your Vs is X here. That's how negative feedback is operating. Okay? This is the same picture that you see here, the same, by putting an RE here, I get a negative feedback. And is this negative feedback, which is, please think about it, now that we have seen that, yes, this is how negative feedback works, if you saw, how was it helping? The negative feedback was distorting what was appearing over here, right? It's causing a distortion in the signal which appears over here between base and emitter. That distortion then gets compensated by transistor's distortion, and you get a nice sinusoid at the output. Okay, very interesting way in which this is working here. All right, so let's stop here.